morning, ladies and gentlemen. My name is Masanobu Kubota from International Institute for Carbon Neutral Energy Research, ICNR for short, at Kyushu University in Japan. It's my great pleasure to be able to present our research here. But I'm from mechanical engineering, so I hope you can find some interesting point in my talk. Today, I'd like to make a presentation about fretting fatigue in hydrogen and the effect of impurity addition. So let me start. This is the outline of my talk, but I'll skip it because of time reason. First, I'd like to tell you about current status of the use of hydrogen in Japan. Here you can see a blue car. This is a fuel cell vehicle which is launched by Toyota in the end of 2014. The fuel of this car is hydrogen. According to some news, newspaper or TV news, Toyota already sold 3,000 FCVs. And this red car is Honda FCV. They announced they will launch this car by the end of next March 2016. So in parallel to the sales of FCV, construction of hydrogen refueling stations is in progress in Japan. Here you can see the map of hydrogen stations in Japan. Now we have 3 commercial hydrogen stations, but more than 80 hydrogen refueling stations will be available by the end of next March. Next, I'm going to talk about home fuel cell system. In Japan, this kind of system already became popular. The number of cells of home FC in Japan reached more than 130,000 this year, and the number is increasing. Unfortunately, hydrogen doesn't provide each home in Japan, so this has a reformer, so it means CO2 is emitted. In this sense, hydrogen is not green or not clean, but the energy efficiency is very high. As I told you, the use of hydrogen is steadily expanding in Japan, but we still have a lot of technical challenges. One of the problems we are tackling is how to reduce cost of hydrogen without compromising safety. Here you can see a guy. He is fueling his car, but this car is FCV, so the situation is very different from gasoline or diesel cars. At the moment, he grasped 70 megapascal hydrogen gas in his hand. The pressure is very high. I feel something danger. And in addition to very high pressure, hydrogen deteriorates material strength. You may know the term hydrogen embrittlement or hydrogen-assisted fracture. So that's why we are studying interaction between material and hydrogen, mechanism of hydrogen embrittlement, design method, etc. So now I'm going to talk about fretting. What is fretting? This ring is hydrogen packing we developed for sealing 100 megapascal hydrogen gas. During research and development of the packing, we experienced fretting. Please look at these figures. These figures show sealing part of the packing. When pressure increases, tip of the packing moves backward, and then the pressure decreases. Pointer doesn't work. The tip of the packing returns to the original position. So the holder, between holder and the tip of the packing, relative slip is produced. The slip amplitude is very small. In this case, it is a few micrometer. When pressure is cycling, this relative slip motion is repeated. This small amplitude relative slip motion is called fretting. This motion, slip motion, causes wear damage, special wear damage. It's called fretting wear damage. And in many cases, the material suffering from fretting simultaneously suffered from fatigue stress. So we call this phenomenon fretting fatigue. What is the problem when fretting fatigue occurs? I'll explain it. This is SN diagram, which is the most basic diagram to evaluate fatigue strength. This figure shows stress amplitude, which is intensity of fatigue load, as a function of fatigue life. We can see two curves. The curve in black shows plain fatigue strength. Plain means no fretting. And this blue curve shows the fretting fatigue strength. As we can see here, the fretting fatigue strength is significantly reduced compared with that of smooth specimen. So fretting fatigue caused many failure accidents so far. So even now, fretting fatigue is one of the major concerns in the design of machine and structures. As I told you, fretting fatigue is combination of fretting wear and metal fatigue. So hydrogen can have influences on both friction wear and metal fatigue. So we should study fretting fatigue in hydrogen to ensure safety of hydrogen equipment. The objective of this study is to characterize the effect of hydrogen on fretting fatigue strength, to elucidate the mechanisms, and to clarify the effect of impurities. Now let's move on to the procedure of the experiment. This figure shows the fretting fatigue test method we used. This yellow bar is fatigue test specimen, and these green blocks are contact pads. They are assembled this way, and then thank you very much. Yeah. Fatigue load is given to the specimen. Then fretting fatigue is induced between contact pad. The material, today I'll show you the result, is austenitic stainless steels. Yes. The test environment was laboratory air, hydrogen and oxygen mixture. The pressure of the gases are 0.1 megapascal in gauge pressure. It's just atmospheric pressure. Now I'll show you the result and discussion. This is a SN curve. This green curve is for the plane fatigue test. And this blue curve shows the fretting fatigue strength of the same material. So first, we recognized the fatigue strength is significantly reduced by fretting. And secondly, we know the fretting, this curve is the fretting fatigue strength in hydrogen. So we know the hydrogen reduced fretting fatigue strength. So we try to elucidate the mechanism. We observed contact pad like this. Before looking at this photograph, please imagine that if specimen and contact pad simply pressed each other, the boundary between pad and specimen should be a straight line here, like this. But this is an observation result. The boundary between pad and specimen is meandering or winding, and some part of the boundary disappeared. We think these are the evidence of local adhesion. And we found many small cracks. So we understand the mechanism that adhesion and following small crack formation are reduced fretting fatigue strengths in hydrogen. But such mechanism can work in other non-oxidative environment. There is no effect of hydrogen. So we continue the study to elucidate the role of hydrogen. So we investigated the crack initiation. Today I don't have the time to talk about the detail of the experiment, so I'll just show you the result here. In air, we didn't find any cracks, but in hydrogen, we found some cracks with some fretting fatigue conditions. So these results clearly indicate that hydrogen assisted crack initiation. So this is one of the reason for the reduced fretting fatigue strength. And we carried out further examination. This material has this size of original grain size, 70 or 80 micrometer in grain size. But we found very, very fine microstructure at the adhered spot. This means that the material at the adhered spot received severe cyclic plastic strain. So this high intensity of plastic strain lead to crack initiation. But not only for crack initiation, this plastic strain causes crystalline structure change. Here you can see the result of electron backscatter diffraction observation of the adhered spot. Again, I say this material is austenitic stainless steel, but we found different crystalline structure at the adhered spot. According to the X-ray analysis, we determined this microstructure, crystalline structure, is strain-induced martensite. So plastic strain changes microstructure. Unfortunately, this strain-induced martensite is vulnerable to hydrogen, although austenite is not sensitive to hydrogen. So this crystalline structure change is also another cause of the reduced fretting fatigue strength. So this is a summary of the mechanism. During fretting in hydrogen, local adhesion occurs and it causes severe plastic strain. It leads crack initiation and it also causes crystalline structure change. And today I don't talk about this issue, but plastic strain enhanced hydrogen absorption into the material. So all these reasons contribute to the reduced fretting fatigue strength. On the other hand, in air, oxidized fretting wear particles separated specimen and contact pad, so strong adhesion cannot appear. By the way, hydrogen fueling to fuel cell contains some amount of impurities. It's not preferable to the performance of the fuel cell, but it's necessary when considering practical use. And we think adhesion is sensitive to impurities, so we investigated the effect of addition of impurities. We choose oxygen as an impurity. So this is a result of the fretting fatigue test. This curve in red is the fretting fatigue strength in the high purity hydrogen. And these curves in green, orange, blue are the fretting fatigue strength in the hydrogen-oxygen mixture. As we can see here, the addition of small amount of oxygen reduced fretting fatigue strength. And the addition of oxygen also changed crack initiation site. These figures show the contact path and the position of main crack. Here we can see in the high purity hydrogen, main crack is located at the contact edge. On the other hand, in the hydrogen-oxygen mixture, the main crack moves toward inside of the contact surface. This change is directly linked to the reduction in the fretting fatigue strength. This is a mechanism. These figures shows contact pressure distribution on the specimen surface. In the high purity hydrogen, the contact pressure, the high stress concentration arises at the contact edge. This contact pressure concentration causes strong compressive stress field on the specimen surface. So this crack cannot propagate. Therefore, the fretting fatigue strength is relatively high. On the other hand, in the hydrogen-oxygen mixture, fretting wear occurs. It changes contact pressure distribution like this. So compressive stress field no longer there. So this crack easily propagates. Therefore, the fretting fatigue strength in the hydrogen-oxygen mixture is lower. To confirm this mechanism, we observed oxidation behavior by the XPS analysis. These graphs shows abundance ratios of iron and iron oxide on the surface. For the unfretted surface, original surface, the signal of the iron oxide is dominant. This means the stainless steel surface is covered by oxide film. This is a result of the in the high purity hydrogen. The signal of iron oxide is reduced. Instead, the signal of the pure iron is increased. This means fretting removed oxide layer. But if the oxygen is added, again, the signal of the iron oxide increased. This means oxidation is faster than the removal of the oxide layer by fretting. This result is consistent with this mechanism and these observations. So this is a conclusion. Okay. So fretting fatigue strength in hydrogen and the effect of oxygen addition was studied. The fretting fatigue strength in hydrogen is significantly lower than that in air. Adhesion between the contacting surfaces occurred during fretting fatigue in hydrogen. The adhesion causes localized severe cyclic plastic strain and transformation of crystalline structure. All these phenomena are responsible for the reduced fretting fatigue strength in hydrogen. The addition of ppm level oxygen drastically changed the fretting fatigue strength in hydrogen. The addition of oxygen changed fretting wear behavior. It resulted change in the stress conditions at the contact edge. As a result, the fretting fatigue strength in hydrogen was reduced. Acknowledgement. Most part of this study was carried out in collaboration with Air Liquide France and Air Liquide Japan. That's all for my presentation. Thank you for attention.